Hey physics students, this is the force diagram. This is the assignment that is actually going by the name of force diagrams number 5. So I hope that didn't cause any confusion for you. Alright, so we want to make a force diagram for basically for that point right there. So let's see, we don't have like a ramp here, so this is not one where we want to make a tilted axis system. We just want to make a regular old XY. So let me do that first. There's my spot there. So I'm actually making the force diagram for this spot, the junction between the cable and the rope, right? So the lava sample that's attached to this, this would be, I'm not going to fuss too much. If you put the force of gravity from that lava sample, it would actually be the force of tension on the, I'm going to say on the junction, because that's what it asked me to do here, from the lava sample. If you called this the force of gravity on the lava sample from the entire Earth, that's fine. I mean, it's the same force. This is just the other end of the rope that's attached to that. So either one of those, I'm going to be happy enough. And they're telling us that that's 125 newtons. Now we got these two other ropes here. And this is 38 degrees. And I'm going to have to break those up into their XY components. Like that. Okay, so now what's equal to what? What we need to do here is recognize that this one down force must be balancing these two ups. So if we split this in half, that's got to be 62.5 newtons here and 62.5 newtons here. They're not both equal to 125 because that'd be 250 up and only 125 down. And that's not what's going on. They're balanced. So if this is 625 and this is 38 degrees, we should be able to set up a little trig to be able to figure out what the tension in the rope is here. And I should have labeled that here. This is force of tension on the junction from the rope. Okay? So what's the trig equation that we need here? This is the hypotenuse of this triangle. This is the opposite side to this angle. So opposite and hypotenuse, that means we're talking about the sine function. So sine of 38 is equal to opposite over that hypotenuse, which is the force of tension that we're looking for. So I'm going to switch those because algebra. And then, let's see, I got a calculator around here. So 62.5 divided by the sine of 38. Just make sure that I'm in degree mode. I am. Well, that's about 102 newtons. Alright, and then for the second one, the actual apparatus has a pulley in the middle of the rope. The cable parallels one side of the rope, goes over the pulley and a lava pool. Reason for this is that simply tightening the rope, like pulling on these, isn't going to be able to lift the lava out. So here's why I calculate how much tension would be needed in the rope to decrease the angle to 5 degrees. So if we wanted to make the angle 5 degrees, the only thing that's different here is that that would be 5 degrees. So I don't have to redo the whole diagram, I think. I can just do this calculation again. So if you wanted to, basically this is the same as asking how much tension would you need to like tighten the rope all the way so that this comes up higher. And if you do the math there, instead of sine 38, just want the sine of 5. So then it goes up to 717 newtons, which I guess we're supposed to think, oh, that's a lot. If you want just kind of a ballpark number, like 717 newtons, maybe you're thinking, well, how much force is that really? It's in terms of pounds, I think more in pounds. If you divide by 5, that gives you a pretty good ballpark for what that is. So it's about 143 pounds of force, something, or 140, something like that. The actual number is, I think, 4.54 is the conversion, but it's an easy just ballpark to, if you divide by 5, it'll give you an idea what newtons are converted into pounds. All right. This guy looks like he's working hard. So we're pulling this box at a constant speed, so that means that the forces are balanced. And there's no ramp. There's a force that's at an angle here, but it's not on a ramp. He is on a flat surface. So that means my axes are lined up like this. And what do we got? We're going to have a force of gravity, of course, on the box from the entire Earth. And do we know what that is? It's a 50 kilogram box times 10. That's 500 newtons. About 100 pounds, according to that little trick I just told you. Pretty heavy. I guess that's why he's sweating. And what else? We have a 200 newton. That's the pulling force, and that's at 30 degrees. So it's a force of tension on the box from this rope, and that is 200 newtons. Okay? Well, before I do anything else, I need to break this up into its components. And before you go putting a normal force in here, a support force that's equal to 500, it's not equal to 500 because this guy is pulling a little bit up, right? Some of this force is in the up direction. This is 30 degrees, so trig, the sine of 30 is 1/2. I know that because I like math. So that's going to be 100 newtons. Of course, you can do it with your calculator if you want. 200 times the sine of 30. Oh, there it is. And then 200 times the cosine of 30. So this is 173 newtons here. Those are the components of that. So if this thing's going at a constant speed, then I know there must be a force of friction on the box from the floor. And it's got to be equal to this, because if we're going at a constant velocity, then forces are balanced. Now, in the up-down direction, it's a little bit more complicated, because I have one down, one up, and then another up from the support force, or normal force, on the box from the floor. And this is 500, this is 100, so this is going to have to be 400. Because 500 total up equals 500 total down. And I know that the forces are balanced. So that's what that looks like. Let's see, I think I probably answered the questions here, but let's go through these and do what we are asked to do. Write an equation for all the forces and components of forces on the box in the vertical direction. So in the vertical direction, I'll do the ups first. I have the normal force plus the sine component of the tension force. Right? That was the sine, the y component of that. Those two had to equal the gravitational force. That's what we're looking for here. I'm not looking for the equation with numbers here, looking for this sort of descriptive equation that says these are the names of the up forces equaling the down force. And then calculate the size of the normal force on the box. What we did was normal force plus, this is 100 newtons here, this was 500 newtons. We just kind of did it by looking at the diagram. So that's going to be 400 newtons. Write an equation for all the forces and components of force on the box in the horizontal direction. So in the horizontal direction, I just have this equals this. This right here is the cosine component of the tension force. And that's got to be equal to this force of friction. And then calculate the size of that. Well, this is 173 newtons. And that's it. Right. Determine the weight of the tram. The cable at the left exerts a 30,000 Newton force. Force of tension on the tram from, let's call this cable 1, call this one 2. So from cable 1, that's equal to 30,000 newtons. And the tram is attached to the cable, so the tension in the left is not necessarily equal to the tension in the right cable. Oops, sorry about that weird spacing thing. So this angle here is 75 degrees. So this angle here would be 15 degrees. And then there's a force of gravity on the tram from the entire Earth. And this is the other tension, which they're telling us is not equal to that. Force of tension on the tram from cable 2. Don't know what that is yet. So no extra questions here. We just have to figure this out. So let's see. What's equal to what? Well, if it's moving, I guess it's not moving, or we would either assume that it's at rest here, because it doesn't say, or that it's going at a constant velocity. In other words, the forces are balanced. So up and down equal each other. Now that doesn't help me figure out the weight of the tram because I don't know what that is, but I can figure that out because those have to be equal. So if this is 30,000 here, then I've got that. I know the angle in the triangle, so I can figure this out. So the force tension in that second cable, what's that equal to? Well, I guess I should write my little trig equation. So this is opposite and hypotenuse. So again, I have the sine of 15 degrees is equal to opposite. That's this over the adjacent. I need to find that first. I guess I could. I guess I don't really need that, do I? So there's a couple ways you could do that. You could find this. That would be cosine there if you're going to go the direction that I was just talking about. But actually, I want this, and I know this. So that's opposite and adjacent, right? And we don't actually ever have to find that if we don't want to. So the tangent of 15 is opposite over adjacent. That's this. What do you want to call that? That's like the y component. I'm just going to call that y for now. And the adjacent is the 30,000. So going to multiply that up there. So tangent 15 times 30,000. $8,040. and that's this. And I feel like, oh wait, but they asked for the weight of the tram. That's the same as the gravitational force on it. Same thing. All right. There's a bear climbing up a hill at a constant speed, so forces are balanced. Now there is a hill here, so that means I'm going to try to match that angle with my axes. And then put the bear right there. Of course, the force of gravity is straight down. Doesn't care about the bear. And I'm going to do my components going over and straight down. That's where the right angle is. And I'm going to do that way, so I'm going to label this force of gravity on the bear from the entire Earth. I'll put that over here. And just looking ahead here does eventually tell us that the bear is at 400. That's a pretty big bear. 4,000 newtons. And look at the triangle. Where's the little 17-degree angle? It's down here. That is not a 17-degree angle. Come on now. Right? And the bear's going at a constant speed, which means there must be a support force, also called the normal force, on the bear from the hill. And that's got to be equal to this. And then there's got to be force. Now this is like the bear's paws, like gripping the hill, so I think you could call that a force of friction or traction, or I guess you could call it force of walking or something. I wouldn't get too upset about that, but I think really it's a friction or traction force would be a better name for it on the bear from the hill. And that's got to be equal to this. So if I break this 4,000 into the two pieces, then we're good to go. We should be able to answer all the questions. So I'm just going to do both. 4,000 times the sine of 17 and 4,000 times the cosine of 17. If I can see both numbers there, I think there's almost no chance that I'm going to mess this up, because obviously this is the bigger one. Also, it's adjacent to the 17, so that's going to be this. Let's call that, how about 3830? Round to that nearest tenth. Do the same with this, 1170. And that means that the force of friction is also 1170, because it's got to match that. And the support force is going to match that. Write an equation that describes the forces that act parallel to the ramp. Parallel to the ramp. Right, same direction as the ramp. That's these. So that would be force of friction is equal to the force of gravity, but not the whole thing, just this piece of it. And that's the opposite times the sine of 17. Write the equation that describes the forces that act perpendicular to the ramp. Perpendicular to the ramp, that's these. So that would be that normal force or support force is equal to the other part of the force of gravity, this part. That's what I'm looking for in those equations. And if the mass of the bear is 400 kilograms, then determine the value of the normal force. That's what we would do here. So the normal force is equal to 4,000 newtons times the cosine of 17. Which we already did. All right, last one from this for this exercise, this assignment. 950 kilogram car is driven up a hill at a constant velocity of 7 meters per second, where 1,200 newtons of friction and drag oppose its motion. Draw a force diagram for the car. Okay, that's on a hill. So I'm going to tilt this, try to match that angle. And that gravitational force is going to get broken up according to our new little axis system here, like this and this, and that's the 22-degree angle down there. And the car is 950 kilograms, so the force of gravity on the car from the entire Earth is 9,500 newtons. And I can go ahead and find those components real quick while I'm at it. 9,500 times the sine of 22, and 9,500 times the cosine of 22. So that's, let's call that, how about if we run to the nearest 10 again? So 3560, that's the smaller one, and 8810. Alright, there's the pieces of that. So what else we got? They're telling us that there is this much friction and drag that oppose the motion. Car's going this way, so that would be another force in this direction. So that gets a little crowded here, and boy, I sure wish I had written that under there now. 3560 newtons, that's that. Because if we've got this other force here, also in that direction, this is not drawn to scale, sorry. That's 1,200 newtons of, I'll just call that force of friction. Air drag is like basically a form of friction, so I'm just going to roll that all together in one frictional force on the car from stuff. It would be like, it's not really from the road because this is not like skidding. It's not that kind of friction. It's friction in the axles, and there's air drag and stuff. So hard to nail that down to one thing. I'm not going to fuss at you if you had something different there. All right, and then of course there's a support force. Normal force on the car from the hill, and you could put the road there. That would be fine. And I know what that is. That has to equal that. So you know that. And then, of course, since it's going at a constant velocity, there must be, this is, what do you want to call this? Force of like traction or something on the car, and that would be from the wheels. Or I guess from the road, if the wheels are part of the car. So something like that. And that has to be equal to, like this direction and this direction have to balance. And I've got two forces in this direction, the 1,200 and the 3560. So this has to be 4760, the sum of those two. All right. What's the weight of the car? Don't say 950 kilograms. That's not a weight. That's a mass. You want to know the weight? That's gravitational force. Same thing. Weight is a force. We measure it in newtons. Calculate the normal force on the car. Show your work. So the normal force is going to be equal to the gravitational force, and that was the cosine component of that. And then calculate the force on the car that allows it to go up the hill. That's this one. So that force of traction, we called that, is equal to the sum of these two. That's the force of friction plus the force of gravity times the sine of 22. So that's my work, right? That's how I set it up. And that's 4760. All right.